Hocam
Evet.
benim f fonksiyonu ile ilgili bir sorun vardı. Biz koordinat sistemi olarak f fonksiyonu
Hı hı.
için ne kullanıyorduk, ben onu
Hı hı.
unuttum hocam da.
Yani f sadece eta'nın fonksiyonu.
Hı hı.
Eta. Eta'da hani dünkü videoya tekrar bakarsan e, eta ve iki tane yani bir koordinat transformasyonu yapmıştık. Xi ve eta diye. Xi aslında x'e eşit. Eta'da işte bir
Y'nin bir
definition
fonksiyonuydu.
var. Y'nin bir fonksiyonu var. O şekilde. Yani aslında farklı iki koordinat. Yani xi aynı da y farklı bir koordinat sistemi. Eta farklı bir koordinat sistemi.
Dünkü videonuzu izliyordum da hocam. Bu
Hı
eksi 0,0904 değerinden
hı hı
biz flow separation'ın
hı
gerçekleştiği
hı
noktayı bulabiliyoruz
hı hı.
demiştiniz.
Hı
E,
hı.
O tam kafama oturmadı hocam, o yüzden benim. Yani e, nasıl buluyoruz? Sonuçta elimizde bir derivatif term var. Biz sadece bunun sıfıra eşit olduğunu
Evet.
biliyoruz.
Şu condition şu. Du dy'ın sıfır olduğu yer. Du dy'ın sıfır olduğu yeri bulmaya çalışıyorsun. Çünkü yani dolayısıyla o da gradient'ın bu şekilde duvara tam 90 derece geldiği noktada sıfır oluyor. Ve bu da şu demek, e, yani teorik olarak bundan daha fazla ileri gidersen akış artık sağ tarafa değil sol tarafa doğru gidecek. En azından belli bir bölge içerisinde. Yani şu bölge içerisinde, separated zone içerisinde. Onun için bunun nereden yani du dy pozitiften negatife dönüyor değil mi? İlk başta pozitif, burada artı, burada negatif, burada eksi. Artıdan eksiye geçerken bir yerde sıfır olması lazım. Sıfır eksenini kesmesi gerek. E, Dolayısıyla o noktaya bir separation noktası diyoruz, şurasına. Yani şöyle bir grafik çizersem bu mesela hani S koordinatı olsun yüzey boyunca. Şu S. Burası da du dy olsun. Bu bir yerde ilk başta pozitif, bir yerde sıfırı kesiyor. Değil mi? Dolayısıyla burası separation noktası oluyor fiziksel olarak. Oraya denk gelen m'i de bulursan o da buna denk geliyor.
Anladım hocam. Teşekkür ederim.
Hı hı. Okay, so let's continue. So we discussed this case yesterday. So, I mean, just to summarize, we first discussed Blasius solution. So this was a solution for for the flow or for the boundary layer around the flat plate, incompressible flow, and most importantly, with zero pressure gradient. So dp dx equal to zero. And then we have seen, basically we obtained we did ordre of magnitude analysis, obtained the simplified equation set, and we solved for the Blasius problem, and then we obtained expressions for delta, delta star, theta, cf, tau wall, for all these parameters. Now, and then we examined the case for the same flow, meaning the flow, laminar flow basically, but now with a pressure gradient that and similar to I mean, using a similar approach like Blasius, meaning having a coordinate transformation. After the coordinate transformation, basically defining what we call a similarity variable eta, and then trying to find this, trying to convert all the physical conservation equations into one single ordinary differential equation. That's what also Blasius did. But for the non-zero pressure gradient case, this is what we got. So sorry, this is what we got here for the non-zero pressure gradient case. And now we have a parameter called m here. And for favorable pressure gradient, as we discussed yesterday, which we call an accelerating flow, and where there is actually no risk of flow separation, m is actually positive. And for adverse pressure gradients, which is the case in which we could potentially have flow separation, so it's decelerating flow near the surface, that corresponds to negative m values. And as I was just explaining to your friend, m value, the gradient, velocity gradient is initially positive, du dy is positive. Within the separated region, du dy is negative. This is the separated region conceptually shown here. And somewhere in between, we need to cross the 0 point. Like if I draw du dy versus s could be the surface length. And we should cross this 0 point here. That point corresponds to a specific value of m, where this is minus 0.0904. If you put this value of m, the second derivative of f function, which is actually related to this du dy, becomes 0. So that's what we call the separation point. And this equation, if you remember again yesterday, we no longer call it Blasius' equation, because this was developed after Blasius. We call it Faulkner-Scan solution, or Faulkner-Scan equation. So this is what we discussed yesterday. And we will discuss a little bit more related to this. The thing is, I mean, until this point, we mainly focused on flat plate, laminar flows around flat plates. This kind of boundary layer solution approach can also be applied to certain, analytical solutions, basically. It can be also obtained for certain kinds of other types of flows we will see right now for a few examples. One of them is called wedge flows. We know what a wedge is. We have seen when we were discussing this semester compressible flow problems related to oblique shock waves and everything. We know what a wedge is. It's this shape here, basically. This shape here is called a wedge. Now, of course, we are in the incompressible viscous flow problem. So we are not interested, and we don't have any shock waves or anything like that. For the wedge type of flow, as it's written over here, generally the edge velocity variation along x can be it's known that we can describe it using a power law, similar to what we used for the Faulkner-Scan solutions. So U edge velocity, so just the velocity at the edge of the boundary layer, varies with x to the m and times c. Now, and c is a constant. Now, what we can do, of course, with this type of external velocity variation, and we know that this external velocity variation is indeed related to external pressure variations through the Bernoulli equation. We have also seen that yesterday. We can also get a similar relation like here, which looks actually very much similar to the Faulkner-Scan equation. Only thing is this beta, the half wedge angle is related to this m parameter if it's a wedge. And indeed, this actually is a more generalized problem. For a certain value of m, which is 0, for example, if m is equal to 0, beta becomes equal to 0. This turns out to be a flat plate, simple Blasius flat plate solution problem. So this case is even more generalized than what we have seen before, and entirely based on this parameter beta, which depends on m. So depending on the choice of m, so therefore depending on the choice of beta, this equation can indeed represent a flat plate with pressure gradient, or a non-flat plate, meaning a wedge flow even, okay? So there are certain cases based on this beta parameter. So we can obtain different types of flows by changing the value of m as it's written here. For example, some values of m between minus 0.5 and 0 corresponds to beta angles between -2 and 0, and this actually physically corresponds to what we call a corner flow. So as it's shown here in this graph. And for certain values of m, for positive actually values of m from 0 to infinity, and for beta values between 0 to 2, this is basically a wedge flow as we know it. And for example, for the specific value for m, which is equal to -1, beta actually becomes minus infinity. This actually corresponds to a sink flow. So as if like you have like a little gap here and the flow is basically draining out from this. So all these three types of flows can be, the boundary layer characteristics of all these three types of flows can be obtained by solving this equation. So this is a quite general equation compared to the Blasius solution. In fact, Blasius equation is a special form of this, very specific form of this equation in reality. And this table, I will explain this table a little bit. So for different values of m, so in the first column, so these are solutions for different types of flows, all these. On the first column, we have m. M assumes a different value. As you can see, in this case, it's 1. This is 1/3, 0.11. We have 0 and some negative values. We have corresponding beta values in the second column. And we have all these relevant boundary layer parameters as written as a function of Reynolds X. So therefore, the numbers that you're looking at here is the constant that we get in those equations. For example, if we focus on the CF equation for just simple case of m equal to 0, which is the Blasius's boundary layer case, CF was equal to, what was it equal to? 0.664 divided by square root of Reynolds X, if you remember. We have seen this previously for the Blasius boundary layer case. So this number 0.664 is here, as you can see. Okay, so and the column is CF times square root of Reynolds X. So CF times square root of Reynolds X gives you this number if it's a Blasius solution. Similarly, delta star divided by, the constant that appears in the delta star equation, for example, for the Blasius solution is this one, and for theta equation is this one, and for delta boundary layer thickness equation is this one. So this fourth row is entirely, it corresponds to Blasius solution because of the fact that m is equal to 0. The ordinary differential equation, this one, gets reduced to basically Blasius equation. So, and we have actually obtained, we have seen the details previously. Now, the thing is, if m is different than 1, each condition corresponds to a different type of flow. One of them, for example, the second row corresponds to a 45-degree wedge flow, okay? So m is chosen as 1/3, beta is 0.5. And then you can see for that type of flow how different these coefficients are. Like the coefficient, the constant in the CF equation, constant in the delta star, theta, and delta. And for example, you can compare them with the Blasius flat plate solution. So geometrically, we are talking about two different cases. Blasius is just a flat plate. So let me sketch here, just a simple flat plate. This one is a 45-degree wedge, boundary layer over a 45-degree wedge. So basically, similar, the governing ordinary differential equation here is similar. So our solution parameters are basically the same. However, the constants are different. You can see, for example, the CF value is about, I don't know, maybe 2.5 times larger in the wedge flow. And let's see this one, for example, this one is smaller. for delta star, and for theta value is smaller for the wedge flow, and also delta value is smaller for the wedge flow. So this means that if you would like to compare boundary layer characteristics of these two physically different flows, I mean not physically but geometrically different flows, I can say, you can compare the coefficients and try to understand that. The first case is called a stagnation flow. It's kind of different than, it's not a flow or a flat plate. It's not a wedge flow. It's basically like it could happen like if you have a flow from left to right, for example, impinging on a plate like that, and then flow gets turned, and then like that. So we call this type of flow a stagnation flow. So somewhere here, the flow, we will have a stagnation point, and around this point, the flow will be deflected left and right, or up towards top and towards bottom. So the boundary layer properties that will form over this type of plate is a stagnation flow. And in fact, it corresponds to a wedge angle of 90 degrees. If you see the beta parameter is equal to 1. And by the way, if I think there was a detail I may have missed. So here the wedge angle is defined. The actual angle is beta times pi over 2, by the way. So when beta is equal to, is selected as 1 over 2 in that table, so this one becomes pi over 4, so it's 45 degrees. When beta is selected as 1, this angle becomes pi over 2, so it's 90 degrees. Okay, so that automatically changes the geometry. As you can see, the first line, beta is equal to 1, so it's basically this type of flow field. So this is 90 degrees to the incoming flow stream. So we call it a stagnation flow. These types of flows are called stagnation flow. We talked about 4, I mean, 3 is somewhere in between, a wedge again, but probably at an angle less than 45 degrees, higher than 0 degrees. Case 4 is Blasius, as we just discussed. All coefficients are Blasius's solution. So that is nice. We directly obtain the same result from a more generalized equation. And the rest from 5 to 8. 5 to 7, I guess, or maybe I cropped up the table. I don't know, but 5 to 7, we have negative m values, and this corresponds to basically corner flow. So beta angle is actually negative. Okay, beta angle is here. You can see negative values, and then for those negative values, we can consider. Yeah, we can see that the different coefficients, and you can also compare these coefficients with the flat plate Blasius solution. So we are talking about a corner flow like that. One interesting case is case 7, where we have this specific number for that m value that we discussed in the beginning of this class. And that corresponds to a certain beta angle, meaning this one times pi over 2, basically. So this is minus 0. What is this? About minus 0.2 times pi over 2. So it is, and it is a minus angle. So I think that for a wedge flow, this is the angle. So it's defined from the horizontal towards the surface. We take so we are interested in this angle here. So it is absolute value of beta 0.2 times pi over 2. That I'm talking about case 7 here. So what is this? So this is pi over 10. So this is pi over 10.
18 degrees hocam.
18 degrees değil mi? Öyle. Pi over 10. So this means that at least this theory predicts that if if this deflection, I can say this deflection angle is about 18 degrees, the CF value, which is related to tau wall value, which is related to du dy value, is 0, which means that the flow separation point is right here at the corner. The flow will separate and probably will not be able to follow this geometry. Just of course, this is just theory for a simple laminar flow. Let me give you an extra information. Generally, when we are designing these types of corners or diffusers, for example, let's say we have this pipe, and then we would like to transition into a larger pipe, okay, or larger channel. Now, of course, we have to connect them like that, okay. Now, if of course there is so all these are kind of corner flows that we have here. So generally, of course, in a real life problem, it may or may not be laminar. If it could be turbulent. Plus, there are more complications. So the general rule, engineering rule that we use is that this half angle must be approximately, I mean, less than 3.5 degrees. Okay. So as you can see, the total deflection should be less than 7 degrees. This is a much more restricted case, as you can see, compared to this one down here. But this is kind of an engineering, I can say, rule of thumb. So whenever if you're in the business of designing channels and different channels that are going to be connected to each other. So actually, these are what we call diffusers here, subsonic diffusers. Then we need to be careful about these corner angles, and we need to keep this angle smaller than in the total angle smaller than 7 degrees. And so that, of course, puts a limitation on the length of this, okay, because that angle is related to the length of this, so that you can use that criteria to determine how long this transition channel or this diffuser should be in your problem without causing any flow separation. So this is kind of practical engineering knowledge, like an aside information. Okay, so but the theory, at least for these simplified cases, meaning a laminar flow over these bodies, is interpreted, I mean, can produce solutions for these types of flows. Here we see velocity profiles. We have seen only one of them before. We have seen only this one for which beta is equal to 0. Let me try to trace it. So only this one here, we have seen this one as the Blasius profile. Okay, Blasius velocity profile. We indeed have U over UE on the y-axis. I mean, this is kind of inverted. Before we have seen X and Y are inverted here. Before, when we plotted this, we plotted F prime here. F prime is basically U over UE on the x-axis. That's how we plotted it before, and eta was on the y-axis, and we said it looks something like that. This is kind of inverted axis values. So here x-axis is eta, y-axis is f prime. So this 0 beta equal to 0 is basically your Blasius solution here, right in the middle. Blasius's velocity profile solution. But for different beta values, you can see how the velocity profile actually looks like. And we indeed know that at this stage, different beta values correspond to different geometries, like wedges, corner flows, stagnation flows. So for different values, you see how velocity profile actually changes. And from negative values, and indeed, this negative beta angle corresponds to, as we have seen, a 0 friction coefficient level here. zero friction coefficient. CF is zero. CF, if you remember, was equal to tau wall over 1/2 rho u infinity square. So which means that tau wall is zero, which means that tau wall is equal to mu times du dy, which means that du dy is zero. Okay, and if indeed, if you look at this plot here, so in this curve, it comes to the wall. By the way, this zero eta equal to zero, here is the wall condition. So at zero, this curve comes at almost 90 degrees, asymptotically curves down and comes at 90 degrees to the wall. So du dy actually is zero. So and it has along this curve, somewhere around here, if you take a look at the second derivative, you can see that there is an inflection point in the distribution. So mathematically, I don't know if you remember, but mathematically inflection points are calculated using the second derivative of the function. So in this function, we if for this specific beta value, we indeed have an inflection point. So this is very typical of a separate, the velocity profile at the separation starting point. This velocity profile generates an inflection point in the function, and du dy becomes zero at the wall. Good, so we can see all these velocity profiles. So for a series of beta values, you can see in this range, you can see how the velocity profiles are changing.
Hocam,
Yes.
I have two questions about the table in the previous slide. Hocam, in the beta and m is equal to 1 case, we have the momentum boundary.
Theta?
Yes.
Momentum thickness.
As lows, is it because flow hits the wall and transfers momentum at maximum to wall?
I mean, theta is the momentum thickness, and therefore this function, theta over x, Reynolds x, and square root of Reynolds x, is a function, if you remember, of telling us how theta grows over this specific type of boundary layer. Yes, how fast it grows. For example, if you compare the theta value of this flow with the theta value of the Blasius flat plate boundary layer, this is about half, approximately half of Blasius. So which means that at a certain x coordinate, the theta momentum thickness will be half of what you would have on the Blasius boundary layer. And the physical reason, I mean, could be, let's say, very roughly explained as you explained. Okay, yes, there is, let's say, very strong momentum inflow coming, and there is a strong stagnation. You force the flow to go to zero velocity, and then, of course, not only that, you force the streamlines to turn 90 degrees to the left and right, or to the top and bottom, and then the momentum gets distributed between these two. And then the development of the boundary layer is, I guess you can explain as you said, there's a very strong, first of all, reduction in momentum, and then regrowth of momentum.
Hocam, also, how do we define x and y coordinates? Because in the Blasius case, we defined the x coordinate as along the flow. But in this case, flow cannot penetrate through the body, so
no, it cannot. So we generally define it like this.
okay.
So this is kind of a rotated version of the flat plate, like a flat plate at 90 degrees angle of attack, maybe, if you want to put it like that. So it is zero if it's Blasius case, and then we keep increasing beta angle, beta times pi over 2, and then we keep increasing and increasing, and at some point we reach 90 degrees. Every time we look how boundary layer grows over the surface, right? At 0 angle, we are interested in how it grows over this surface. At a wedge angle, at a certain wedge angle, we are interested in how it grows over this surface. And at 90 degrees, how it grows over this surface after the stagnation point.
So basically we are doing a coordinate transformation
Rotation.
Okay.
Coordinate transformation is something else. This is basically rotation of coordinates.
My another question is, hocam, in the CF values, tabulated values, after the after a certain m number, we have CF as 0, and in this case, flow gets reversed across the boundary. Sorry, at the wall. For this case, do we have CF as negative or as continuously 0? Because
no,
you
no,
said
it's
that
after the
separated.
separation point. After the separation point, let me go back here. After the separation point, the velocity gradient is negative, and therefore tau wall is negative. Therefore, CF is also negative. It doesn't remain at 0. Okay.
Okay, hocam, teşekkür ederim.
Anyway, so we extended. It's good that I'm on this slide right now to recap. So we extended. We started with this Blasius, and we extended it quite a bit with the Faulkner scan, based on the Faulkner scan equation, which is kind of a modified version of the Blasius equation. But based on this and based on the introduction of this angle beta parameter, now using a similar approach like Blasius, meaning that after this coordinate transformation plus I'm coming up with the similarity variable and also definition of the stream function. If you remember, we also did that. We now get this general equation, which potentially can represent all these kinds of flows and laminar flows over all these different geometries. Good. So now we will. I will try to explain something more. I mean, the thing is, everything we dealt so far. I mean, it's also written here. Everything we dealt so far is basically relatively simplistic geometries. Yes, flat plate, some simple wedges, flat plate at 90 degrees or whatever. But of course, in real life, we generally have to deal with more complicated geometries. Okay, so as it's written in the first sentence here, so far we investigated these what we call self-similar solutions. Self-similar solutions meaning the just to remind you from yesterday, if you have a developing boundary layer over a flat plate, the velocity profile at different stations actually, when similarity parameters are used, they all show one single function. So that's what we call a self-similar solution. And those were on simple geometries. However, if you're interested in a more general geometry, we may not be able to find an analytical solution like this. So, as the question is asked here, what do we do then? Then, for those cases, we generally use what we call integral methods for boundary layer analysis. Integral methods. So, what does that mean? So, from this point on, we will also start learning this one, integral methods. Until this point, our entire, everything that we learned was based on basically differential equations, right? First, reduction of partial differential equation set to an ordinary differential equation, to a one single ordinary differential equation, and trying to obtain solutions for that. But now we will discuss something different. We call it integral methods for boundary layer analysis. Now, as as explained here, what do we want to know? I mean, when for a general geometry, of course, we are. Why are we interested in this boundary layer theory? As we have been discussing since the beginning of this viscous flow related subject, of course, the first thing that the first reason that we are interested in is we need to know skin friction coefficient because it is related to uh, drag coefficient over that body. So viscous drag. So skin friction coefficient is of interest for us. Plus, we would like to know if there is going to be any flow separation or not. Okay, we would like to know that. And plus, we would like to know boundary layer properties. Here it's written delta, but also we would like to know delta star and theta as well, because especially delta star will help us, for example, if we want to use this effective body concept and you make use of some implicit solutions and everything. So, therefore, in order to obtain this, now we propose another methodology. So everything that we are interested, all these quantities, CF, tau wall, delta, delta star, theta, all of these, as it's written here, are what we call integral quantities. Okay, they are we obtain them after as a result of some integration. So this is just at every x location we have only one single, for example, delta value or delta star value. We do not have, for example, delta star distribution along y at a certain x, for example. That's completely out of context. We don't have anything like that. So these are integrated quantities. Everything, delta star, delta, theta, CF, tau wall, everything is integrated quantities. So if we are interested in obtaining these integrated quantities, maybe we can develop what we call an integral approach, and which could potentially be applicable to any geometry, not only to flat plate or wedge or those simple geometries, to any geometry that we can think of: airfoils, wings, aircraft. Okay. So in order to do this, our starting point is again, of course, conservation equations, but now written in integral form, not in differential form. So therefore, we would like to obtain what is written here, the momentum integral equation for boundary layer analysis. This is something different. So we are not really after obtaining like an equation like Blasius or Faulkner's scan. We are not after that. We are after obtaining some kind of equation for integral quantities, not an equation for u or v or p, but for integral quantities starting from integral conservation equations. How do we do that? So it takes a few slides for its derivation. I would like to go over them, but anyway, I may not be able to finish them today. We will continue next week, but let's start. So first, let's remember our conservation equations written for a boundary layer again. Again, I mean, our starting point is the differential equations for a boundary layer. So boundary layer equations, not the Navier-Stokes equations in general. Boundary layer equations that we obtained after this order of magnitude analysis. So this is what we are seeing here. We have the conservation of mass equation, du dx plus dv dy equal to 0, which can also be rewritten like that. Du dx is actually equal to minus dv dy, plus conservation of momentum along x, for example, it looks like this for a steady flow, basically. And so therefore we do not see the time derivative term, plus this is x momentum conservation. The y momentum conservation is again the same, dp dy equal to 0. Since we are dealing with boundary layer equations, not the full Navier-Stokes, but reduced boundary layer equations, dy equal to 0 is indeed the y momentum conservation. We know that. But so these were our starting points. So we would like to integrate this, integrating the momentum equation. So this one from 0 to h to some distance above the solid body surface, and h, let's say, is a value greater than the boundary layer thickness. So we do one by one, term by term. 0 to h integral, first term, and we are integrating along y, so dy, and h is also along y. And the second term, and the pressure gradient term dp dx, and the viscous term nu times d square u dy square dy. Okay, and let's take a look at the so all of them. Let me check. Sorry, let me quickly check. Yeah, this, I think this equation is the same here. All of them has to be integrated along y. And first, let's investigate the second term. For example, where is my pen? So this term, second term on the left-hand side. 0 to h v du dy. So mathematically, we decompose it into two parts. I mean, I would like to take v inside the derivative. So 0 to h, the d dy of u times v dy. And of course, when I do that, I have to subtract the corresponding term. 0 to h, now u times dv dy must be subtracted. And so when integrated, this will give me some u times v value from 0 to h. And now u dv dy value, and there must be a dy here, I guess, here. But we know that dv dy is actually equal to minus du dx from continuity, from previous slide, if you remember. Here, dv dy is equal to minus du dx, so I made use of this. And so u times v is, of course, on the wall. Both of them are 0. At h, let's say it will be equal to u edge times vh. The value of v velocity at h, we don't know what that is. So it becomes equal to this, u edge times vh plus this integral. Okay, now let's consider the continuity equation like we have seen in the previous slide. Now I would like to obtain an expression for this one, or for this one. I see a u times du dx term. And from the continuity equation, I have this. If I integrate both sides of this equation, 0 to h du dx times dy, and minus 0 to h dv dy times dy. So this becomes actually, integration of this is just integration of dv from 0 to h, as is written here. So it's just v value at h minus v value at 0. So v value at 0 is 0, no slip condition on the wall. So it's going to be equal to minus vh. Well, we also have, so this entire thing, not entire thing, but this u du dx, which is kind of similar to this, is actually equal to minus vh. We also see a vh here. Let me continue one more slide and we will stop for today. So basically we can replace that second term. What we are trying to do, just to remind you again, we are trying to find a better expression for the second term in the equation. And now we reached this one. This 0 to h v du dy can be written or can be replaced by this equation, minus u e times vh. But instead of vh, I write this one. So this is vh, or minus vh, but minus sign is here, plus 0 to h u times du dx dy. And just taking all of this and replacing it taking this out of the original equation and replacing it with this equation gives me this one. So as you can see, this was the first term on our equation. As you can see, the first term here. So this remains. The second term, we replace it with whatever we got here, with this one. So the first term plus the second term will be equal to whatever I have on the right-hand side. So the right-hand side I kept the same. So now I can combine, because look what we got here. First of all, I have this term and this term are exactly the same, but they are added. So I have two of them. So 2 times u du dx dy. So these two are combined here, minus this term. Okay, and then the right-hand side remains the same. Anyway, as I told you, we ran out of time. The derivation is not finished, but what I'm going to do next time is to, first of all, I will summarize what we were doing and quickly go over the derivation again, same things again, but quicker this time, since we already discussed them until this point. But the derivation is not finished yet. We will combine some of these terms together and then try to reach this, what we call momentum integral equation for the boundary layer. So let's stop at this point, but I will start with a summary of what we did regarding this derivation to remind you next week, and then we will continue our derivation. Okay, so let's stop here. Do you have any questions?
Hocam ben bir şey sormak istiyordum ama dersle alakasızdı.
Dersle alakasız.
Evet.
Peki, o zaman özel bir şey mi?
Yani aşırı özel değil de yani daha çok beni ilgilendiren bir durum, o yüzden soracaktım size.
O zaman bunu durduralım. Herkes çıksın, sen sor.
Tamam hocam.
Bir saniye.